Okay, hello. So this is your lesson for Wednesday and Thursday when I'm gone, and it is going to cover something called the Châtelier's principle. If you want to say it with a very aggressive French accent, please do so. Named after, of course, the scientist who kind of coined this, figured this out, all of that. Okay, the Châtelier's principle. So this whole idea of equilibrium, we've started, and you guys just know the basics so far. You know how to do a KSP expression, etc. But now we're going to talk about what those actual changes are that might throw something out of equilibrium. So when a reaction is at equilibrium, sometimes it can get messed up. So the reason why, it's going to be funny at first, okay, you're going to say is because life sucks, okay? Now, what we mean by this, I remember when I was in AP Chem and Mr. Cantor walked in while Miss Alman was teaching and said this to us. Life sucks, meaning there's always something that's going to happen. The universe trends toward chaos. That's what we call entropy. And there's actually mathematical ways to calculate entropy, and we're going to get to that all later. You'll do it in AP Chem. But for now, I just want you to know life sucks, meaning you're not going to stay at equilibrium. So if you don't stay at equilibrium, that means you're going to have to change the reaction, or rather the reaction is going to have to change itself to balance out whatever change or stressor is being applied to the reaction. So let's do some examples of this. Sorry, grabbing notes. Okay, so let's do some of this. A couple things that are basics that can change a reaction would be concentration, temperature, and change in pressure or volume. Okay, so things that can change it. I still have to think about effect and affect every single time I write it. Things that affect equilibrium. Okay, pressure and volume, temperature, concentration, so meaning, we change the actual concentration of something. Remember when we first did our equilibrium expressions on Monday, Tuesday, and I told you that you can basically not include solids and liquids for a specific reason? This is why. Their concentrations don't really change. Think about something solid or a pure liquid, right? Those concentrations aren't going to change. Concentration can change for gases and things that are dissolved in water or ions, such as something aqueous. So that's the reasoning of why. All right, so those are the three main things, and then we'll see how all of these types of changes affect the reaction and what the reaction does to correct itself. So let's say I have something like this, A plus 2B, and that's going to give us C, just like that. So what would the reaction do if I make some different changes? Okay, let's talk about a first one. What if I add more of substance B? It doesn't actually matter what it is in this case. Okay, second one is going to be if I add more of C. And the third would be if I remove A. All right, so those are three basic changes. We'll start with that. So if I add more B to this system, that means that this whole situation right here is going to be higher. So there's more B. We're going to shift to the right so that we can make more of this B into C. So in other words, if we add more of this, we have to shift away from it. Okay, so I'm going to say this would be a shift to the right. Okay, so if I add more of B, the reaction is going to shift in the direction of products to get rid of that extra B that I just added. Okay, seems weird at first. You'll get the hang of it. It's actually pretty intuitive once you kind of do a few of them and get the hang of it. Okay, more C. So same thing, except we're on the other side. So now for this guy, if I add more C, that means I'm adding a higher concentration of this. Okay, so there's going to be more of this. So that means I'm going to shift away from it, again, to the left this time, to get rid of some of the C. And now we're going to make more A and B from the C to balance it out. So this one would be a shift left. Okay? Okay, now what if I removed A? If I take A out completely, I remove it, this is immediately going to try to make more of A because all of a sudden there's this gap that needs to be filled. You can think of it that way. If there's no more A, we're gonna have to go in this direction to the left to produce more of the A. Okay, so this one would also be a shift left. All right, so there's some basics to start off with. I'm going to walk over here and make sure my camera is capturing all of this. Cool, it actually looks good. All right. All right, so that is a basic start. Let's do a couple more. So what if I actually have a real equation this time? Okay. All right, so what if I have N2 plus 3 H2s? Okay, we can assume that these are all gas, A, because they're diatomic, and B, because if I don't specify that something's solid or liquid, you can assume it's aqueous or gas. Okay, equilibrium arrows, and we've got 2 ammonia. All right, so let's say I want to do H2 is added. Okay, let's say I want to do N2 removed. Okay, let's say I want to do, let's add some HCl to this. Okay, and then what if I add O2? Okay, okay, so if you want to pause it here for a second and then try to maybe do those, you can, but this is only a second example, so if you can't yet, it's totally normal. All right, so if I add H2, I'm increasing this concentration right here on the left side. So I'm adding more H2, this is gonna go up. So that means that this reaction should shift to the right to make more NH3 to get rid of some of that H2 to balance it out. Okay, so if I am adding extra of this, the reaction should shift away from it to balance it out. So this should be a shift to the right. Okay, give it a pause there for a second so you can kind of understand everything that's going on. Okay, so then if N2 gets removed, if I'm removing this, I've just created this gap, this hole. So now this reaction should shift to the left so that it can start making N2 again to fill in the gap that I've just created. It's almost like if I've created a little hole, we've got to patch the hole, okay? So remember when I was telling you, we're gonna be doing a lot of this. Sometimes it kind of helps to actually do this while you're doing this and like kind of do this back and forth. I don't know why, but that does help. All right, so again, if N2 is removed, I've now created a gap here. That means we're gonna go towards it to fill in the gap. We're gonna create more of our reactants from our product instead of the other way around. All right, so this one would be then a shift to the left. Okay? Okay. So this one's an interesting one. What if I added HCl? So if I add HCl to this, I'm gonna be making NH4Cl. This should actually have been part of what I told you in the beginning. I wouldn't necessarily at this stage of where you're at in chem expect you to fully know that right off the bat. So if I added HCl, I would be making NH4Cl, okay? So imagine that I'm adding that somewhere in that reaction, okay? So what we're gonna do is, this is gonna shift to the right. The reasoning why is because the HCl is going to steal some of this NH3. So if I add HCl and it wants some of this, it's gonna be pulling this over towards it, okay? It's gonna be stealing NH3 away to make the NH4Cl. So if I'm essentially taking the NH3 away, that means I'm gonna shift to the right because this reaction pertaining to all three of these things up here is going to, again, try to fill in the gap, try to fill in the hole. So I'm going to say this is a right shift or shift right, doesn't matter. Shift right, because again, the HCl that we add is going to be taking away NH3s. Okay, so effectively adding HCl decreases NH3. And so if we're decreasing the NH3, our reaction has to shift in that direction to turn more of our N2 and H2 into NH3 as product to fill in the gap that we're creating, okay? All right, so there's that. All right, and then our last one here is adding O2. And so same thing, this is part of the what I would give you. So this is all given. This is about to be all given as well. So if I add in O2, it's going to make water. Okay, so if it's making water and we have O2, it's probably combining with this H, right? So if I'm adding in O2 this time, it's going to be pulling the H away. So if I'm creating a gap right here, removing H to make water, because we've added O2 to the system, I now have a gap here on the left side. So we should shift towards the left in order to fill in the hole that we just created, okay? So this would be a shift left, like so, okay? So again, one more time with these last two because they are a little bit strange, okay? If I'm adding in HCl and it's making NH4Cl, again, you're given that whole thing, the HCl is going to be taking away the ammonia. Okay, so if I'm taking away ammonia, I'm creating a gap where the ammonia should be. So my reaction will go towards the ammonia to make more of it, to fill in that and correct that. Okay? Then, for that last one more time, okay, I'm adding oxygen to make water. So if I add oxygen and I'm making water, I'm using that H2 to make water, right? H2O. So I'm taking this away, I'm creating a hole where H2 is. So if I'm creating a hole there, we need to shift towards that again to patch the hole, so to speak, to make more of the H2 to put it back because we're taking some of it out to make water. All right, so hopefully that makes sense there. Okay, I'm gonna pause there, erase and rewrite some new stuff. So bear with me for 1 second. Okay, for this next one, changes in temperature. So another thing that can be changed besides concentration, like we just kind of went through, would be change in temperature. So let's say I have this reaction here, and you guys know from the heat unit that we just did, okay, your negative and positive delta H's. You for sure know about those. Remember that negative delta H would be heat lost or released, okay? Positive delta H would be that heat is gained or absorbed, okay? So another thing you may want to add is products and reactants here, okay? So let's take this as our example, and then I'll kind of explain a little more. So if I have A plus B is giving us CD plus heat, okay? Heat is on the product side. Okay, so not only do you know heat is part of the product side, so this is a heat producing or heat releasing reaction, you also can tell that based on the sign of your delta H, which happens to be negative as well. So those are two ways you could tell. So let's say that the change that I'm applying for Le Châtelier here is to decrease the temperature. So if I'm decreasing the temperature, that means heat's being taken away. That means I have a hole on the right. So you can think of heat as the thing, the substance that's being decreased or taken away. So if this is now producing less heat, the reaction is going to go in the direction of heat producing to fill in the hole that we just created. So if temperature is decreasing, that means heat is on the right side. Now there's a hole on the right side, okay? So if there's now a hole there because we're taking away heat, decreasing temp, our reaction is going to shift to the right in order to produce heat to balance out. So this would be a shift to the right. All right. Okay, again, I'm going to pause and erase and all that. Okay, just wrote another one up there. All right, so for this one, okay, we have heat as part of our reactant side this time. That's how this one differs from the one you just did. So heat is on the reactant side, and we also can tell that we have a positive delta H there telling us that it's endothermic, right? It's being absorbed, all of that. So if I cool the container down, I'm effectively taking away heat from the left side. that means there's now going to be a hole there. That means my reaction is going to shift to the left towards that change so that we can produce more heat to balance out the heat I'm taking away when I cool the container. So because again, we're cooling the container, we know this is endothermic, we know the heat is on the reactant side on the left here. I'm going to cool the container, I'm going to take away this heat. That means that the reaction will go towards it to the left in order to balance it out. Okay, so the converse is also true. When I increase the temperature, now I'm going to have extra heat in this area. So I'm going to have more heat than I did before. Well, equilibrium, we're going to try to balance it out. I'm going to get rid of some of the heat by creating more CD, okay, away from the side with the heat. So if I add more of that, just like with concentrations, we got to go away from it to get rid of something. So I'm going to, if I add more heat or increase the temp, either way you can say that, then I'm going to shift to the right this time to get rid of some of that extra heat. So away from the heat producing side. So right shift for that one, okay? All right, and that is the basics of heat. Okay, our last big thing that we can do to change a system would be to change the pressure or volume. This really only pertains to gases because those are those are two things that affect gases rather than the aqueous stuff as much. So you are only going to look at gases for this. Okay, so for pressure and volume, okay, this is really important. If I have more space, I can hold more stuff in it, right? So that means if I have like a bigger volume, right? Or a decrease of pressure making more volume, okay? If I have more space, I can hold more stuff. And in this case, we want to think of stuff as moles. So if I have more space, I can hold more moles. You can also say stuff if you want, if that kind of is easier to just start off with and remember, okay? And then if I have less space, that means I have less moles or less stuff. Okay, so those two changes, whether they increase or decrease, you can kind of figure out what's going to happen based on these two principles here. So here's a reaction. We know these are gases because they're diatomic. Also, if I tell you what the phase of matter is. So let's say I want to increase the pressure. If I increase the pressure, okay, think about like I don't have one right here, but remember from the gases, right? Water bottle, okay? If I increase the pressure by squeezing it in, right? I'm creating less room for stuff. Less room for stuff. Less room or less space, right? For stuff. So we're gonna shift to the side where there is less stuff. So over here, I have 3 moles plus another mole. Okay, so this side has 4 moles of stuff. Okay, this one has 2 moles of stuff. Okay, and by stuff, again, we're talking about moles and we're talking about the specific containers. So I'm going to shift towards the one that has less stuff in it because I have less space or less room for it. So I'm going to shift towards the sides with 2 moles, so to the right. So again, I'm increasing pressure. That means I'm decreasing volume at the same time, right? Remember, we did this whole idea, Boyle's law? Okay. So, again, if I have less space for stuff, I'm going to shift towards the side with less stuff because I naturally don't have as much room for it, okay? Now, if we increase the volume, now I all of a sudden have way more room for stuff. So I have more space or more room. So I'm going to shift to the side with more stuff because now I can hold all that stuff. So I'm going to shift left. All right? Okay? And then, the converses of those are true as well. Important note as well, if you have the same amount of moles on both sides, increasing the pressure or volume will not change it. So you can say if moles are equal on both sides, increasing or decreasing pressure and volume produce, you can say no change. Okay? Two other things that produce no change: catalysts, no change, and something like if we added, let's say we added neon or argon, right? Any of the inert noble gases, that wouldn't change it either, okay? So catalysts and noble gases also don't change it. All right, and that's going to be the end of the first video of me explaining all that to you.